Welcome back to the deep dive. We're continuing our exploration of the OEIS for all you number theory students out there. Today we're looking at A000337. The formula looks pretty straightforward. AN_NM1 plus 1. But like many things in math, there's more to it than meets the eye, right? It seems to connect some really diverse areas.
That's exactly right. It's a great example. The formula itself, N1, 5 plus 1, seems simple enough. And the first few terms start out, 0, 1, 5, 17, 49, 129. But these numbers, they actually tell a much bigger story. It goes way beyond just, plugging numbers into a formula.
Okay, so 0, 1, 5, 17. Where does it get really interesting? I mean, how does that formula somehow connect to something like binary numbers? It doesn't immediately scream digital.
That's one of the first really neat connections. It turns out this sequence precisely counts certain features in binary strings. Stephen Penrice pointed out that AN is actually the total count of zeros you find if you list out all the binary numbers from 1 up to a number that's just n plus 1 ones written out.
A string of ones, so like 111n plus 1 times.
Exactly. And Emmerich Deutsch found another layer. It's also the total number of bits, ones, and zeros in the binary numbers from 1 up to a string of n-ones.
Wow. Okay, so it's counting fundamental binary properties. That's quite a link from the formula.
It is. It kind of gives you a measure of how many zeros are packed into blocks of binary numbers. A really fundamental link, like you said, between the sequence and, computing basics.
Incredible. But you mentioned it pops up elsewhere, too. It's not just binary and number theory. Where else does A00000337 make an appearance? Maybe in, like, shapes or structures?
Oh, definitely. If we zoom out a bit, you find A000337 in combinatorics, for instance. It counts something called directed column-convex polyominoes, basically specific ways to arrange squares on a grid when they have an area of n plus 2 and meet certain rules.
Polyominoes. Okay, like tetra shapes, but more specific.
Sort of, yeah. Different rules.
Yeah.
And it gets even more abstract. In graph theory, AN3, for n greater than 1, gives you the genus of an n-dimensional cube graph.
The genus, so like how many holes it has if you imagine it as a surface?
Precisely. Think about how many handles you'd need on a donut shape to draw the graph without lines crossing. It's amazing how these concepts connect.
That really is stretching across different fields. Now, thinking specifically as number theory students, are there properties within the sequence itself? Like, are the terms prime or composite in interesting ways?
Yes, that's a great question for this audience. Jonathan Vospost noted something fascinating here. For certain values of n, like 2, 3, 7, even 27, AN turns out to be a prime number.
Prime, just from this formula.
Yes, but then for other values of n, say n equals 4, 5, 6, 8, it gives you semiprimes.
Semiprime, so the product of exactly 2 primes.
Correct. So the sequence itself flips between generating primes and semiprimes. And figuring out why it does that is, a really interesting number theoretic puzzle.
That is intriguing. So many facets. Are there other ways to define it mathematically? Maybe a generating function or a recurrence?
Absolutely. There's quite an elegant generating function, x, 1 2 by 2, that gives you a sort of closed-form analytical perspective. And it also follows a linear recurrence. AN, 5a in H1, 8a in 2, plus 4a in F3, at least for n bigger than 2. So you can calculate terms from previous ones.
Okay, so it has that algebraic structure, too.
It does. And maybe one more neat connection, this one from Enrique Navarrete, it's combinatorial again. AN is the sum you get if you take all possible subsets of the numbers 1, 2, 2 up to n, find the largest number in each subset, and add them all up.
Wait, let me wrap my head around that. So for n3, subsets of 1, 2, 3, you take the biggest number in each one, like 1 from 1, 2 from 2, 3 from 3, 2 from 1, 2 from 1.
Exactly. And 2, 3 gives 3, 1, 2, 3 gives 3. Add them all up, including 0 from the empty set, and you get 17, which is a 3.
Right, 17. Wow, okay. So let's try and pull this together. We started with n1 plus 1, simple enough. But we've seen it count zeros and bits in binary. It describes features of polyominoes. It gives the genus of cube graphs. And it even generates primes and semiprimes, has neat algebraic forms, and relates to sums of maximums and subsets. That's quite a journey for one sequence.
It really is. And I think the key takeaway for you listening is to really consider this. How can one formula, seemingly so basic, act as this kind of hidden thread linking totally different mathematical ideas, binary code, geometric shapes, the fundamental nature of primes. It's all connected through A000337. So the thought to leave you with, what other simple sequences out there in the OEIS might be doing similar profound work connecting disparate fields, just waiting for us to see the full picture?